Thank you, Nakamoto-sensei, for gracious introduction. Good morning. I'm glad to be here on this special occasion. I'm Hirota from Kyushu University. Today, I'd like to talk about sensors for advanced safety, comfort, and convenience in future transportation systems. First, let me give you my brief overview of my career. I joined Nissan 1987 and worked on advanced automotive technology for 30 years, mainly at the research center. I came to Kyushu University 2017. I would like to state in advance the content of today's presentation includes both my achievement during my time at Nissan Motors and my achievement since coming to Kyushu University. I would like to introduce my research so far. I spent most of my research time on LWIR sensors and their applications. Since coming to Kyushu University, I have been working on research into preventing crossing collisions. And we also hold infrared array sensor forum every July. Many infrared technology experts gather and exchange ideas. Here is an outline of my talk. I'll begin with social changes and then give you on movement towards environmental protections. Next, I'll talk about improving safety performance. After that, I'll describe the result of our research, crossing collision analysis and prevention, and LWIR sensor and the application. After that, I'll briefly deal with driver sensing, and finally, I'll finish with short summary. First, let's consider demand for transportation. This graph shows GDP per capita and annual travel distance. As you can see, travel distance grows with GDP growth. Urbanization and economic growth are creating rapid increase in the demand for mobility in daily life and economic activities. Next, let's look at the number of automobiles produced, which supports transportation demand. This graph shows trend in motor vehicle production from 2000 and 2023. Global motor vehicle production is approaching 100 million units per year. This trend has been influenced by various factors, including global economic situation, Lehman shock or COVID-19 pandemic, changing in demand, technological innovation, and environmental regulations. I would also like to look at the number of vehicles in use. This graph shows trend of vehicle in use from 1973 to 2023. The number of vehicles in use worldwide has increased to approximately 1.6 billion in 2023. Car penetration in non-OECD countries has accelerated since 2000, shown here. This is due to progress of urbanization and expansion in the middle class. On the other hand, in Japan, the number of motor vehicles in use has increased to nearly 81 million, but the rate of increase is low, shown here. Next, trends in annual sales volume by automaker is very important in understanding the performance of industries. The annual sales of Toyota Group reached approximately 11 million units in 2023. Toyota continues to grow steadily due to its strong hybrid technology and popularity in emerging markets. Automakers are growing bigger through the alliance, consolidation, and cooperation. In 2021, Fiat Chrysler and Peugeot Citroën merged to form Stellantis, world's fourth largest automobile manufacturer. So this slide shows a capital alliance between Japanese automakers. Toyota and many other Japanese automakers has capital alliance and technological partnership shown here. Nissan, Renault, and Mitsubishi Motors shared technological development and market strategy through the alliance. Consolidation is progressing rapidly against background technological innovation and global competition. Next, looking at the CASE. CASE is an acronym for Connected, Autonomous, Shared and Service Electrification. CASE represents 4 important technological trends in the automotive industry and symbolize the future transformation of mobility industry. Each CASE technology is developing individually, but they will interact with each other and form the next generation of mobility. I'll explain the history of CASE very briefly. The concept of connected cars began to develop in the late 1990s and early 2000s. Research on autonomous driving technology began to attract serious attention towards commercialization after 2000. The concept of car sharing itself was born in Switzerland in the 1970s, but began to take off in the earnest in the 2010s. In particular, emergence of ride-sharing service such as Uber and Lyft has brought about major revolution in automotive industry. CASE is an indicator that symbolizes change in the automobile industry. In this presentation, I would like to talk about it from broader perspective and use coordinator axis shown here. Until now, automobile has response to social demands by aiming improve their basic performance and being attractive as a products. The major areas of social demand are improvement in the environmental performance and safety performance. From now, I would like to talk about it using this indicator. This is a summary of social changes. The increase in mobility demand is accelerating. The number of automobiles produced worldwide is once again approaching 100 million per year. The automotive industry tried to maintain its competitiveness by deepening collaboration. Automobiles have responded to social demand by aiming improve their basic performance and being attractive as a product. CASE symbolizes transformation in the automotive industry and is expected to have a major impact, not only evolution of automotive industry, but also the nature of the mobility and economic structure of society. Now move on to the protecting global environment, this region. First, look at the fuel consumption trends. Improving fuel efficiency is an important factor in automobile industry. The graph on the left shows the trend of fuel consumption of JC08 mode in Japan. Trend toward improved fuel efficiency is driven by advancement of variety of technologies as shown on the right. Red bold line shows average of trend. Average fuel efficiency has improved significantly in recent years of around about 40%, but is likely to plateau after 2020. Trend in the fuel economy regulation are important topics will have major impact on the automotive industry energy policy. 2030 fuel efficiency standard was announced as a new fuel efficiency regulation, which aims to improve fuel efficiency of new cars by 25%. Japan is also proactive in introducing hybrid and electrical vehicles, and a policy to effectively ban the new gasoline-powered car sales by 2035 is being also considered. Fuel efficiency regulations have become important policy tools to reduce environmental impact and expected to continue to be strengthened. Carbon dioxide emission regulations for automotive are also important for environmental policies. The EU as a region has strictest carbon dioxide emission regulation for automotive in the world. After 2035, the EU has set policy to virtually ban the sale of new cars with internal combustion engines, ICE, and all new cars must be zero-emission vehicles. I move on to the hybrids. In 1997, Toyota released the Prius. The Prius, the world's first mass-produced hybrid vehicle, marked a new start in the popularization of electrical vehicles. Technology innovation in the lithium-ion batteries led to significant improvement in the driving range of EV in the late 2000s. In response to this, Nissan released the Leaf in Japan 2010, and the era of full-scale EVs has arrived. Range extender EV and series hybrid, which are equipped with engine-based charging mechanism, has been developed to compensate the drawback of electric vehicles, such as their short driving range. Battery EV run by rotating motor with charge electricity, as you know. Battery EV made of specialized parts, lithium-ion battery, AC motors, inverter, and onboard charger shown here. As shown in table on left, there are mainly 4 EV charging standards. In Japan, the most widely installed are CHAdeMO. Japan's CHAdeMO takes a lead and aims to be the de facto standard. However, in recent years, there has been a trend toward increasing number of high output Tesla superchargers. Wireless charging technology is also being developed to improve usability of EVs. However, wireless charging is not yet widespread use because of its low efficiency and high cost. Our laboratory researched the optical type shown on the right. So there are 3 main types of hybrids: series hybrid, parallel hybrid, series parallel hybrid, shown here. In the series systems, the engine is only used to store electricity in the battery, and the car is driven by entirely motor. So the acceleration and ride field are the same as in pure EV, battery EV. And in the parallel system, the engine is the main driver when driving, with the motor slowly playing a supporting role. By driving motor during starting acceleration, when engine is under load, fuel consumption can be reduced. The series parallel hybrid is also known as a split system because it uses the engine and motor appropriately depend on the driving conditions. The system motor is alone. The system land motor alone when starting at low speed, and then starts engine when under high load and high speed. DHS system was first adopted system in the first generation of Prius, shown on lower right, and it's still used today as a main hybrid system. This table classified electrical vehicle by power source and drive methods. The right side shows cars use the engine as a main power source of power, while the left side shows the cars use a motor as a main power source. These parallel hybrids and series hybrid systems have become more widespread to take advantage of EVs. I think the system left is the most likely to make the most of characteristic of an electrical vehicles. And I think that's largely due to the reduction in cost battery and inverters. EV shift is a trend to automotive industry that refer to shift from ICE vehicle to EVs. As global environmental regulation are strengths and response to climate change are urged, many automakers and governments are rapidly promoting the development of and the spread of EVs. In particular, increasing number of countries, regions announced a policy to ban the sale ICE vehicles by 2030 or 2035, which are accelerating the shift to EVs. As of 2023, the number of electrical vehicles owned worldwide is expected to reach over the 40 million. In particular, China was world's largest EV market. Has been strong growth in EV sales, with 8.1 million new EV registration in 2023, shown here. This growth expected continues, with EV expected to account for 35% of new vehicle sales worldwide 2030. Today's cars are equipped with many parts made with MEMS technologies. Many of these are engine-related parts. In recent years, if all new car sales were to be battery EVs, many of MEMS parts would become unnecessary. But will this actually happen? From my experience of driving the Nissan Leaf as my personal car for years, I don't think this will happen. I would like to briefly explain some of the reasons. Actually, I have written 2 opinion pieces for Nishi Nippon Shimbun, a local newspaper in Kyushu areas, regarding the spread of EVs. I listed in issues of EVs on the slides. Even 5 years after my first article, the challenges, issues of spread of EVs has not changed significantly. I believe the EVs are suitable for travel with their range, that is short distance travel, and are intended to completely replace, not intended to complete gasoline-powered vehicles. This year, the shift to EV shift began to slow down. New car sales has fallen sharply following the end of subsidies for EVs in EU. In response to this slowing down in battery EV demand, automaker has revised their outlook for EV production and sales, shown on the right. This slide shows my anticipation for future electrical vehicles. Main driving force will be motors. Sustainable suitable battery capacity will be between 10 and 30 kilowatt hour, and the EV has an onboard charger. The capacity depends on the segment due to its battery's high cost. At high speed, direct driven by engine is suitable, I think. This is a summary of protecting global environment. Average efficiency in Japan has significantly improved by about 40%. Rapid shift to EVs has been occurred since mid-2010s, but this has slowed down since 2024. Demand for MEMS sensors will be decreased with the spread of EVs, but will not disappear completely as the engines are expected to survive. Various types of electrical vehicles are expected to coexist. I move on to improved safety. This region. In Japan, the number of traffic fatalities rose to more than 10,000 a year in late 1980s. In response to this situation, Japanese government promoted the ASB program, JNCAP, and amendment of Road Traffic Act. The number of traffic fatalities has been decreased since late 1990s. Since 2000, further advanced in automobile safety technologies, airbag, ABS, and electronic vehicle control, etc., has led to sustained decline in the number of fatalities. In 2022, the number of fatalities nationwide in Japan was 2,610, and the lowest level since statistics began to be collected in 1948. This is a classification by type of car accident. When I classify traffic accident by type of accident, rear-end collision are most common, followed by crossing collisions, which together account for more than half of all accidents. When focusing on the accident involving fatality and serious injuries, crossing collisions are most common, as shown on the right. Recently, Subaru has announced the rear-end collision involving vehicles equipped with their eyesight systems has been significantly reduced by 84%, shown here. So, rarely in the collision accident are decreasing due to widespread use of collision prevention device. The crossing collision are expected to exceed rear-end collision in the late 2020s. So now move on to the GNCAP. Automobile assessment is a program for evaluating safety performance of automobiles and provide consumers and automobile manufacturers as an objective indicator of automobile safety. GNCAP is assessment in Japan. It started 1995. Collision safety performance has implemented in 1995, and preventive safety performance is since 2014. In collision safety performance, there are 3 types of tests for occupant detection and 2 types of tests for pedestrian detection, protection performance, as shown here. Occupant detection includes frontal collision and offset collision and side impacts, and pedestrian protection for head and leg. Next, move on to the preventive safety performance. There is mainly 5 menus. This shows preventive safety performance estimates began 2014. In recently, the number of test items for autonomous emergency braking system performance evaluation has been increased, shown on the here. Following nighttime pedestrian and bicycle testing, as also has been added in this menu. This is GNCAP roadmap and roadmaps 2024. According to this roadmap, the item will be strengths and evaluation pedestrian autonomous braking systems, shown here, and crossing collisions, and driver monitoring systems. It has been revealed evaluation will be strengths, especially nighttime pedestrian. So it's likely to need for LWR cameras will increase. ASB program. ASB is a prototype vehicle being developed for the 21st century with the aim of making automobile highly intelligent through the application of electrical technology. Significantly improve safety as a vehicle driven by a driver and helping prevent accidents and reduce the damage. It will equip the various sensors shown here, computed device, etc., and monitor the driver's vehicle and surrounding conditions, and it's designed to support driving. The ASB project has launched in Japan in 1991 by Ministry of Land, Infrastructure, Transport and Tourism, and has conducted until its 6th phase. Actually, I joined phase 1 and phase 2, and Nissan proposed nighttime pedestrian warning system and blind spot pedestrian detection system. This shows safety equipment has developed through the ASB program from the 1st to 5th phase and has been put into the practical use production cars. Autonomous driving. SAE, Society of Automotive Engineers, It defines the stage of driving automation. Level 3, the driver, the vehicle performed all driving operation under certain conditions. The driver does not need to monitor as long as the system is in control. In 2020, Honda's Legend was the first commercial vehicle certified as a level 3 autonomous vehicle in Japan. ADAS and AD, Advanced Driver Assistance System ADAS, which shares many technology with autonomous driving AD, also become more widespread ahead of the autonomous driving. AD requires more advanced environmental awareness, highly accurate self-location estimation, and highly accurate judgment. Therefore, dynamic map and quasi-zenith satellite are being used, shown on the lower right. Today's car equipped with many sensors, many cameras, many radars, many sonars, and other devices to detect different objects shown here. Radars for detecting car heads, and cameras for lane detection. Radar and camera is detecting for pedestrian, as shown here. Autonomous emerging braking system is a system to automatically brake the vehicle when it's approaching the obstacle and the vehicle in the front. Millimeter wave radar and molecular cameras are mainstream shown here. This is the actual car. Actually, this car is currently my own car, personal car, Mercedes A180. And this car has 5 millimeter wave radars and triple camera shown on the right, lower right, and 12 sonars for parking assistance. These camera, dual camera, stereo camera is for lane detection, and this molecular camera is for taking a picture, movie, videos from in front, shown here as air navigation, and also used for traffic signal recognition systems. The around view monitor is an advanced parking assistant system installed in automobiles, and technology for can be monitored image around the vehicle as shown in the front above. The around monitor system consists of 4 cameras and 4 corner sensors and 2 units and 1 display indicated these figures. But there is an issue has been remained, and resolution of varies depend on the location, and the image are misaligned as a scene shown here. This is a summary of improvement of safeties. Automobile safety performance improving by the ASB and GNCAP. And the widespread use of automatic braking systems will reduce rear-end collision and vehicle-to-vehicle accidents, and the overall number of traffic fatalities will decrease. There are still accidents related to blind spots and difficulty to detect with current sensors. Efforts are needed to reduce crossing collisions. Next, I'd like to introduce the crossing collision, research activities on crossing collision prevention. Crossing collision are second most type right now, and crossing collision are expected to exceed the rear-end collision in late 2020, as I mentioned. Prevention of crossing will become more important. We investigate the crossing collision where we are crossing collision occurs first. More than half of the crossing collision occurred between residential road. Residential road means the its width is 5.5 millimeter or less. And between the residential road and major road. So here. So many of them occurred at a small one-lane intersection. Cross collision at a small intersection on the residential road. So here. So ITADA provides us web map of residential road accident map. So we decided to use this map, and there is, as shown here, there are comparison of accident residential road in the four major metropolitan area of Japan, Tokyo and Osaka, Kobe, Nagoya, and Fukuoka. Zooming at Fukuoka City has more accident on the residential road than other large cities. Shown here, purple shows the highlight. The Hakata, around Hakata station, the area is relatively big. So we decided to proceed the analysis and the judge analysis, and in the focusing on the Fukuoka city. In this study, we surveyed more than 10,000 intersections out of 30,000 intersections in the Fukuoka city, including intersections where accident occurred and accident-free intersection next to accident intersection here. To analyze the characteristics of each ward, first classified based on the number of accidents in the intersection in Fukuoka, Hakata ward, and Chuo ward. This slide shows how to analyze the factor of crossing accident based on the intersection's environment. Environment factors consist of planar elements, traffic control element, and visibility limited element shown here. From our analysis of Hakata and Chuo ward, we found the crossing collision are most likely occurred inter-crossing roads and signal light, single signal light and push button signal light intersections, and setback of stop line is have an impact on crossing collisions. And survey on we are continuously survey on visibility limiting factors. We surveyed on the direction of travel at the accident, and car-to-car accident from the crossing car from the both sides is almost same, but car to bicycle in case the type B bicycle coming from left is much, the number of accidents is much bigger, larger than coming from right side, shown here. This is caused because limited visibility may be contribute to this results. This is a summary of a factor influencing the crossing collision accidents shown here. Then we also focus on the fact intersection accident in Fukuoka City are concentrated at certain intersection shown here, and the intersection accident could be reduced by avoiding certain conditions. Therefore, we create the minimum number of accident routes that minimize the number of intersection accidents and on the route and the destinations. And compared with the minimum number of accident routes with the shortest distance routes in 3 areas shown here. The average length of least accident route was about twice as the length of the shortest distance route. Okay, move on to the infrared AWI sensors, the applications. I'd like to explain why we focus on AWI technologies. The graph on the left shows spectral radiant existence from black body at various temperatures. Surface temperature of a human body is about 305 Kelvin. Therefore, spectral distribution of human body is like a blue curve according to Planck's law. And wavelength of maximum value of around 9 microns. The figure on the left shows transmittance of atmosphere. There are 4 transmission bands, among which LWIR band from wavelengths 8 micron to 13 microns shows good match with radiation emitted from the human body. And we also tested taking the image, test the image of the LWIR and SWIR cameras. And next, I'll explain the difference between LWIR images and SWIR image. Here are 2 images taken with cameras. When we to detect human body with LWIR camera in the dark, it's not necessarily eliminate the object. And the background of image with the LWIR camera is very simple. It is easy to recognize human body. That's why we focus on the LWIR technology. This slide shows, in this slide, I'd like to explain the comparison of infrared sensor, resistive barometer, selective barometer, and SOI diode has high sensitivity, and selective barometer has no DC response, and requires optical chopper modulator in center right. Here. And productivity of hybrid structure of ferritic barometers and vanadium oxide is not high. On the other hand, some couplers does not require chopper, optical chopper, and temperature control, and fabricated by the conventional CMOS IC process. We have interest in these characteristics and focus on the improvement responsivity of sound pipes. Look at the resistive barometer first. This is type utilized temperature variation resistive materials such as vanadium oxide amorphous silicons. And the proposed device structure shown in lower left. Recently, pixel size was reduced from 50 micron to 12 microns. And Full HD having a pixel of 1920 by 1080 R8 was announced. This is SEM image of resistor bolometers. Next is ferroelectric bolometers. And the type utilizes temperature variation direction constant of ferroelectric ceramics, such as vanadium, strontium titanate. The temperature of ferroelectric materials must be kept around the phase transition temperature to obtain high variation of the direction constant. Proposed device structure shown on the right. The hybrid structure consists of diced ferroelectric ceramics and silicon readout IC as used. Each pixel has own transistor for access control. This is a diagram and SEM of image. This is a photograph of ferroelectric camera. We used these. Let's move on to the SOI diode sensor. This type temperature variation induced by forward voltage drop of diodes. 8 diodes connected in series are enhance the sensitivity. Device structure shown on right. Diode fabricated in the SOI layer. These are image of SEM image and the diagram. This is a SEM image of pixel and image taken with FPAs. Last type is sample. This type utilizes the big efficient of sum couples. Each pixel consists several pairs of sum couple and access transistor. Device structure and shown on right. Here is a micrograph. NEC is 128 by 128 sample array. This FPA have CCD scanners. This slide shows Nissan's 120 by 80 samples. These are the images taken with this FPA and the specifications shown here on the right. And small cameras was fabricated, the 48 by 40 elements, very small size, and adopting package with zinc sulfide lens. This camera has non-contact temperature control. Non-contact temperature measurement functions. Chinoan has begun to sell these small cameras as a result of joint research of Nissan and Chino. The world's first modular body surface temperature checker, shown on right, released in 2008. This is the specification and image of Full HD camera, Full HD infrared camera shown here. This is a AWR sensor roadmap. Currently, 12 pitch Full HD FPAs has realized with high-end product. And development continues toward 5 micron pitch in the future. It is expected low-cost Full HD FPAs will be realized in the near future. In the middle class, 30 micron pitch, 4800 pixel FPAs has been realized, but its future is not expected to reduce 25 micron pitch. And AI, recent years, use of AI in the LWL field has been considered. Data set has been provided several organizations. Further development are expected. The optics. Optical system cost of LWL camera is high and difficult to achieve mass production benefit so technological innovation are necessary. Showing difference between the SWIR and LWIR. This table shows LWIR materials characteristics. Among these materials, chalcogenide glass is a material that attracts attention because it can be molded and its refractive index not too high. There is some result of glass and AZC's integrated window seal is type attract attention for nighttime pedestrian detections. So we are considering making of the traffic mirror, which are widely used. LWL camera and traffic camera mirrors detect road, crossroad conditions as shown here. Reflected LWL image obtained both glossy surface and non-glossy surface aluminum foil shown here. Invisible cameras, we can't detect, we can't catch a sharp image. On the other hand, LWL image is very sharp. So this difference between reflectivity of the two wavelength regions. The application we are now considering the LWIR mirror horn at a long distance, flat and hemispherical LWIR mirror shown here. So the IR sensors applications, many automotive sensing systems used in the IR sensor have been proposed shown here. This slide shows nighttime vision enhancement is night vision. Lower is left is LWIR, SWIR system shown on the right. This system is proposed in the first phase of ASB programs, and I think it's one of the earliest efforts. This system intended to give a driver visual assistance by detecting infrared radiation emitted to human face. One major drawback, distance cost of infrared camera is too high. This is GM system. GM launched its night vision system in 1999. This is the world's first infrared system to be used on production cars. Honda has announced the intelligent night vision system in 2004. They equip its pedestrian detection with a function use stereo image processing, shown here, based on the result of the SB2 program. Also, BMW also developed night vision system, which announced in 2005. Unlike GM, which displays on the IR image on the display, in BMW system, IR image displays on navigation system, monitors. And Toyota announced a night view system using SWIR 2002, shown here. This system captures image area in front of vehicle illuminated SW lights, shown here. And we also, Nissan developed a blind spot warning system in the second phase of ASV program. This system consists of a small 48 by 30 element infrared sensor mounted in the four corners of the vehicles. And if a pedestrian in the front and the direction which vehicle is about to move, this system issues the warning and also prevents the vehicle from starting off a movement directions. Next, I'd like to describe a rear view camera system with infrared functions. So let's skip. And we also demonstrated and the exhibition in the ESB. And we also developed the human-machine interface system called IR Commander. This system allows the driver-controlled audio system to navigation system by means of detection of simple finger movement, shown here. We exhibit people at Tokyo Motor Show 2005. And we developed the advanced air conditioner system using the infrared sensors. So next, lastly, driver sensing technologies for driver condition. This technology is used as AD technology, ADAS technology supporting driver easily. So it's expected for, so we are developing onboard device system, but recently wearable device such as Apple Watch has widespread use. So in the future, wearable device, a combination of wearable device and onboard device is promising. Summary, this is a summary. Thank you very much.